Thank you. Okay, let's let's begin. Let the stragglers straggle in. Okay, how is everybody doing today? Good, I hope. I hope you're staying healthy and staying safe and staying in. So, okay, let me know if you have any questions about anything. Okay, I am uploading these recorded lectures to YouTube, so you know you can view them at the link in Canvas. So try to utilize that. Okay. Okay, triple integrals today. Okay, so we're going to move up from double integrals to triple integrals. Okay. The triple integral of f over the box B. Now, the domain is a box now. Okay, this is your domain. Is a box. It's a three-dimensional box. Okay, and then we're integrating over that three-dimensional box to get a four-dimensional function. Okay, some sort of four-dimensional function now. Okay, when we start talking about going into higher dimensions, it's hard to picture. That's why we kind of picture the domain and then integrate over the domain, because the domain we can picture as a three-dimensional figure. In this case, it's a box B. Okay, we're going to get into where it's not a box. Okay, where it's a little trickier, but you know, a box or a rectangular prism, okay, is just like the rectangle that we were dealing with in double integrals. Okay, so they have nice defined, you know, limits, you know, like 0 to 1, 0 to 2, right? -1 to 1. Okay, they're really nice. So we have a box, okay, B, okay, is, okay, the triple integral over B, okay, of f of x, y, z, okay, dv which is equal to, okay, I'm just going to put what it's equal to underneath it. Okay, the limit of LMN as LMN goes to infinity of, and then we're going to have three summations now. I equals 1 to L. That's not an L. Okay, I equals 1 to L. J equals 1 to M. Okay, and K equals 1 to N. Okay, of F of Xi, Yj, Zn, okay, delta V. Now, instead of a delta A where it was over an area, now we're integrating over a volume. Okay, and so again, we're getting into that fourth dimension. Okay, which again is kind of hard to visualize. Okay, but the math always precedes the application. Okay, there are very few cases where the application, okay, you know, defines the math. Exponential growth is one of them, where the application was needed for compound interest, and so the math was developed around it. But in a lot of cases, we develop the math, and we carry this big, you know, tool around with us for a little while before we get the application. Now you can let your fourth variable be time. Okay, and so this is, you know, what would happen if a solid, okay, which is what we call a three-dimensional figure. Okay, some solid is moving with respect to time. Okay, and you can think of that. This has applications in fluid dynamics. Okay, so think of a fluid moving, okay, in and out of a pipe, in and out of a river, you know, where the river meets the ocean. Okay, and you know, saying that, say it's a exhaust from an engine, okay, where it's not just coming out, you know, maybe we have a muffler on that where we're getting some back pressure, right? And so we want to model, you know, what's happening to that fluid over a three-dimensional space, but in real time. This is changing. Maybe the pressure is changing. Maybe we want to know, okay, how is this spilling into the next system? So there are applications. Again, the math was developed before the applications, but that sometimes is the case. Okay, there's two fields of mathematics. There's pure mathematics, which is what I studied in college, and then there's applied mathematics, which the applied mathematics is all the stuff that the application precedes the math. So there's a role for both. So anyway, that's a little bonus for you. Okay, but again, we do have applications today, but at the time it was kind of just a thought experiment, I guess is what you can say. Okay, which is a lot of the math that gets developed. It's a thought experiment until we were like, oh, this fits here. So anyway, okay, let's get into our first integration here. Okay, so let's evaluate, okay, a triple integral over a box B, okay, x, y, z squared dv, okay, where B is equal to, okay, x, y, z okay, this is my domain, such that 0 is less than or equal to x, which is less than or equal to 1. Okay, -1 is less than or equal to y, which is less than or equal to 2. So my x's go from 0 to 1, my y's go from -1 to 2, and my z's are going to go from 0 to z, which is less than or equal to 3. Okay, so again, a nice rectangular solid, okay, or what we call rectangular prism. It's just a box. Okay, so you've got your box here. Okay, your y's are going, your z's are going from, let's start with the z's. Z's are going from 0 to 3. Okay, your y's are going from -1 to 2, and your x's are going from 0 to 1. And so we get our nice little box here. Okay. Okay, that's not what I want. Okay, so that's not what I want. Okay, I want it to go out 1. There we go. Up 3. Okay. So you get the idea here. We want to go out 2. Okay, so this is my domain. This is not the solid that we're looking for, it's the domain. Domain B, which we call a box, because obviously it is a box. It looks like a box. It's because it is. Okay, so let's set up the triple integral here that we want to evaluate. Okay, so 0 to 1, okay, -1 to 2, and 0 to 3. Okay, of x, y, z, and these are all changing, right? X and y and z are all changing. Okay, and so I'm going to integrate in reverse order. Okay, kind of like what we've been doing before with the double integrals. We generally put dy before dx because okay, but in this case, I'm going to do dx, dy, dz. In this case, you don't have to. When it's over a box, you can do it in whatever order you want, because they're just numbers. Okay, we'll get to where it's not a box, and then the order doesn't matter in that case. Okay, so there are easier orders than others. Okay, in this case, the order doesn't really matter that much. The order of integration, you just have to make sure that your limits are nested in the correct order. So the 0 to 1 should go with the x here, which is the innermost integration. Okay, and then next, because we have -1 and 2, is our middle integration. That should be dy, and then our outer integration is dz. Okay. Okay, so we want to integrate on with respect to x first. Okay, on x. So this is going to be 1/2 x squared, and y and z squared are treated as constants. And I'm going to plug in 0, 1. So this just becomes 1/2 y z squared. Basically get a 1/2 and eliminate a variable. So it's kind of nice. Okay, so now I'm going to integrate this from -1 to 2 of dy. Okay, so this is going to be integrating y. So that's going to be y squared over 2. So this becomes 1/4 y squared z squared from -1 to 2. Okay, plugging in 2 for y, we get 1/4 2 squared. Okay, which is 4, so that those cancel. Okay, z squared. Okay, minus okay, 1/4 times -1 squared, z squared. Okay, so this becomes z squared minus, and then this -1 becomes positive, and we get 1/4 z squared, so that's minus 1/4 z squared, which becomes 3/4 z squared. Okay, and so then we're going to do our last integration on z, okay, from 0 to 3. Okay, so this becomes 3/4 times z cubed over 3. 3's cancel, evaluated from 0 to 3. And so we get 3 cubed over 4, which is 27 over 4. Okay. Okay, any questions on our first example? Okay, so what happens when our volume, okay, our volume is not a box, okay? We're gonna make it, we're gonna go increasingly more and more complex, okay, for the volumes that we're, or the solids that we're integrating over. Okay, so let's step it up one more step. Okay, and if it's not a box, then we just say that it is a solid. Okay, it's a solid, it's a generic solid, and we're going to let E represent that generic solid, that domain. Okay, E is our generic domain, just like D was our generic domain for a double integral. E, which makes sense because it comes right after D, I guess. Okay, E is our generic domain for a triple integral. Okay, so number 2 here, evaluate. Okay, the triple integral, okay, over E this time. Okay, z, we're just going to have z dv where, okay, E is the solid tetrahedron bounded by the 4 planes. Okay, x equals 0, y equals 0, z equals 0, and the plane x plus y plus z equals 1. Okay, so let's look at E. Okay, what is E going to look like? Okay, our domain. Okay, in this case. Okay, well, it looks like everything's positive, right? So it's bounded by x equals 0, y equals 0, z equals 0. So we're kind of you know, limiting ourselves to one octant in this case. Okay, the positive octant. Okay, and then you know, how can I draw this this plane x plus y plus z? Well, what happens if I let the find the locations of this plane, okay, on the axes? Okay, so you know, keep x, but let y and z go to 0, then we get, you know, 1, 0, 0, right? So we're looking for specific points on this plane. Okay, and if I can get 3 points, which are going to be the intercepts, okay, 1, 0, 0, 0, 0, 0, 1, 0, and 0, 0, 1, then I can get the intercepts here. Okay. And so this is the plane, okay, that I'm looking at. Okay. Okay, makes sense? Okay, so this is X, Y, and Z. Okay, so we got to figure out our limits, right? I mean, the hardest part of this is just figuring out the limits. Doing the integration should be pretty simple, okay? But we have to figure out the limits. What are the limits here of integration? Well, we know that Z goes from 0 up to this plane, okay? This slanted, okay, plane that's creating one of the faces of the tetrahedron that's slanted. The other 3 faces of the tetrahedron are, you know, basically perpendicular because they make up the sides of our octant here. Okay, but the one that's slanted is this guy here. Okay, x plus y plus z equals 1. So I can actually solve for z, okay, letting z equal 1 minus x minus y, and that tells me that z goes from 0 to 1 minus x minus y. Okay, it goes from that floor of z equals 0, which is the xy plane. Okay, so that's the floor. Okay, so the floor is the xy plane. And then it's going to go to that slanted ceiling, which is the z equals 1 minus x minus y. Okay, and so we have our z here, and then so we're integrating with respect to z first. Okay, getting the height here first. So that's going to be a dz. Okay, so now I have to figure out, okay, well, what am I going to integrate with respect to next? Okay, and we've integrated with respect to z, so kind of that height integral. Okay, and now I have to integrate with respect to x and y. Well, I have to figure out what's happening in the xy plane, right? So we kind of eliminated one of the dimensions, and so we're actually going to talk about the projection of this plane in the xy plane, the projection of the side of the tetrahedron here in the xy plane, and that's going to go down a dimension to d. Okay, right? Because once I have the integration of this with respect to z, it just becomes a double integral. Okay, and then the domain for x and y is just d. Okay, it goes down a dimension. And so what does the domain for x and y look like? Well, it's just this guy that is the line, okay? It's the area created by the line going from 1, 0 to 0, 1. So that's 1, 0, and that, I said it, but I wrote it backwards. That's 1, 0 to 0, 1, right? So this is basically the base. Maybe I can put it in a different color. Okay, this is the base of my tetrahedron here. Okay, so we're getting the base of the tetrahedron, okay, right here. And so we need to set up some equations, or an equation that represents this area, right? So what's the boundary of this area? Well, that's the equation y equals negative x plus 1, okay, or 1 minus x. Okay, so we can say, oh, okay, if we take our vertical slices here, okay, so take a vertical slice, we say, oh, y goes from 0 to, okay, negative x plus 1, or 1 minus x. Okay, and so that's dy. Okay, and then what is dx? What's dx in this case? Well, x just goes from 0 to 1. Okay, so we finally get down to a number, okay, in that one dimension. Okay, so I eliminated the z, okay, dimension. Then I eliminate the y dimension, and then I finally get a function in terms of z. So I get a one-dimensional, okay, and domain for my integration. So I went from 3 dimensions to 2 dimensions to 1 dimension. Okay, so again, one of the hardest parts of doing this is setting up the limits of integration. Okay, once you get that, the integration should be, fairly straightforward. Okay, so let's go ahead and do the integration here. Okay, so z on dz is going to be integrated to z squared, evaluated 1 minus x minus, whoops, I don't know why I'm putting it there. Okay, from 0 to 1 minus x minus y. Okay, so this just goes in. Sorry, it's 1/2. Okay, this guy just gets plugged in there, and we get 1/2 of 1 minus x minus y. Okay. Okay, and then that's squared. Okay, and so now we have to integrate this. Okay, integrate this from 0 to 1 minus x. Okay, with respect to y. And then we've got our 0 to 1 out here with respect to x. Okay, so let's integrate this guy. Well, I don't want to have to square this thing out, so I'm going to use a u sub. Okay, so let's do a u sub. U equals 1 minus x minus y. And so du equals something dy, right? Because we're integrating with respect to y, which means that 1 and x are treated as a constant. So what happens when I take the derivative of a constant? Well, those go to 0. Take the derivative of negative y, that just becomes negative 1, and so it becomes negative dy. So I'm just going to move the negative to the other side. Negative du is equal to dy here. Okay, and so okay. So I'm going to put my limits of integration here, and I will change my limits on this one. Okay, if u, okay, if y is equal to 0, okay, or u of 0, basically, if y is equal to 0, we plug 0 in here for y, then what do we get? Well, we get 1 minus x, right? So that becomes 1 minus x becomes my lower limit. Okay. And then u of 1 minus x, what does that become? Well, that would be 1 minus x minus 1 minus x. So you're taking 1 minus x and you're subtracting off 1 minus x, right? 1 minus x minus 1 minus x, which is 0. You're just taking the same thing, and so it's kind of like the limit swap. And I have a 1/2 u squared negative du. I can put that negative in front, negative du. Well, what happens when I reverse the order of integration, yeah, it makes that negative turn into a positive. So we get 0, negative, sorry, 0 to 1 minus x of positive 1/2 u squared du. Okay. So now we want to integrate. So this becomes 1/3, nope, doesn't, becomes 1/6 u to the third evaluated from 0 to 1 minus x. And so we can just plug in the 1 minus x and the 0, and we get 1/6, okay, times 1 minus x to the third power. And now we have to integrate this from 0 to 1, okay, dx. So again, I don't want to have to multiply that out, cube that all out. I could if I really wanted to, if you just remember Pascal's triangle, it's not too hard. Okay, but I don't want to do that. I'll do another u sub here. U equals 1 minus x, du equals negative dx again. Okay, our limits get flipped again. Okay, so this becomes 1 to 0 of negative 1/6 u to the third. Okay, du, flip those back and make it positive. And we get 0 to 1 of 1/6 u cubed du. And so this becomes, okay, 1/24 u to the fourth. From 0 to 1, plug in the 1, and we get 1 over 24. Okay. Okay, let's take it up one more step. Okay, so our volume is, we started with a volume that was a box. Then we started with a volume that was kind of this solid tetrahedron. It's kind of nice. It has, you know, some nice sharp corners there that allow us to get some really nice domains. Okay, and so now let's take it up another notch. Okay, and we're gonna see what happens when we're still getting kind of a nice figure here, a nice result. Okay, nothing too crazy, but we are gonna have to jump into polar coordinates. Okay, so let's attempt this one. Okay, evaluate the triple integral over e, okay, of the square root of x squared plus z squared dv, okay, where, okay, e, okay, is the region bounded by the parabola, paraboloid, okay, not a parabola, it's his cousin Lloyd. Okay, the paraboloid, okay, y equals x squared plus z squared, and the plane, okay, y equals 4. Okay. So we're going to evaluate this triple integral. Okay. Now, we could make this integral a little bit easier by swapping variables. Okay, if I wanted to swap the variable z for y, okay, it might make this a little bit more intuitive. Okay, it's still not too bad. you know, just know that, you know, basically this is your paraboloid, but it's not a paraboloid in the z direction. Okay, it's a paraboloid in the y direction. Okay, so it's your paraboloid here in the y direction. Okay, we're out here at 4. Okay, because that plane of y equals 4 is kind of cutting this off. Okay, until we get this paraboloid, it's in the y direction. Okay, x, y, and z. So just know that your projection of this in the two-dimensional plane xz is just going to be a circle of radius 2. Okay, y radius 2, because you're going to get projected here. Okay. Okay, so it's kind of like we're rotating the axes, you know, from a z-oriented graph to a y-oriented graph. And, you know, here's your projection. Oops, that's really bad. Okay, and there's your projection. This would be your D domain. Your E is the whole thing. D, once I get rid of the variable y, so I am going to integrate with respect to y first here. Okay, to eliminate the third dimension y. Okay, and so again, you know, it might have made more sense intuitively to swap y and z, but I think it's good to stretch your brain a little bit sometimes, as well as say, hey, you know what? They're not always going to be oriented nicely. Okay, and so, or traditionally in the way that we've been dealing with them. Okay, so so we know that x squared plus z squared equals 4, right? X squared plus z squared equals 4. That's what happens when y is equal to 4, right? That's this circle here. Okay, and then the projection of that is, okay, this is that's the that's that paraboloid. Okay, but when it's equal to 4, okay, that's just going to be a circle, okay, of radius 4 in the xz plane. Okay, let x squared plus y squared equals 4 be the projection onto the xz plane. Okay, and so it's just a circle of radius 2. Okay, that's going to be handy when we eliminate this variable y first. Okay, so what do we got here? Well, we've got the square root of x squared plus z squared, right? And then we're going to integrate with respect to y first. Okay, so where does y go from? Right, where does y go from? Well, it goes from, okay, let me use a different color here. It goes from, if I take a slice here, okay, kind of this horizontal slice, y goes from the function of the paraboloid to the plane y equals 4. So it goes from x squared plus z squared up to 4. And it should make sense that our limit does not contain a y. Okay, why does our limit not contain a y? Because we're integrating with respect to y, and then we're going to plug in these values that don't contain a y so that I can integrate with respect to those variables after this, right? So, so yeah. Okay, so then once I've integrated with respect to y, I then want to integrate okay, this domain D, okay, we've changed our domain, our solid domain E into, we've got rid of that third dimension, and now we want to go, the whole domain here, the whole solid is E. Okay, this whole thing is E. Okay, we're eliminating a variable to get now to D. Once we've, you could think of this as, again, kind of nesting these, okay, integrals, right? So once I do that thing, then I have to integrate with respect to the domain D here, okay, going down a variable. And so what is that? Well, that's just a circle in my XZ plane, right? And so that's a circle in my XZ plane and of radius 2. And now you see why polar coordinates are going to come in real handy here. Okay, if I could draw the circle. That's a really crappy graph. I'm going to try over again. Let's try it this way. 1, 2, 1, 2. A little extra time makes things a little nicer. Okay, and okay, still not great, but it's better. Okay, and so we have a circle of radius 2, right? A circle of radius 2. Okay, so if I wanted to do, and it doesn't matter if you do X or Z, I'm going to eliminate the Z first and then get rid of the X, and then eliminate the X at the end. Okay, so we're going to go dz dx here. Okay, so now what are my limits of integration for Z? Well, in rectangular coordinates, again, this is x squared plus z squared equals 4, right? And so if I solve for z equals plus or minus the square root of 4 minus x squared. Okay, the minus would go on the bottom. That's this bottom curve right here. That's the minus. Okay, and then the top curve would be the plus. Okay, so the plus, it looks like an X. The plus would be the top curve. Okay, and so basically we're splitting it into two curves because you have to, otherwise it's not a function. Okay, so basically the bottom function is the negative, right? So negative square root of 4 minus x squared. The top is the positive 4 minus x squared. Okay, and then what does x go from? Well, x is now, we're limiting it to one dimension, and it goes from -2 to 2, right? So -2 to 2. Okay, so we have it set up. Again, I don't really want to have to integrate with respect to this square root. I don't want to have to plug in these limits of integration. They're not too nice. They're going to become a lot nicer. Okay, a lot nicer once I plug in polar coordinates here. Okay, so let's see how we can do that. Okay, so we have x squared plus z squared, right? X squared plus z squared dy. The problem is I don't have, okay, and we could say that x squared plus y, or sorry, x squared plus z squared in this case is equal to r squared. Does that make sense? Okay, x squared plus z squared is equal to r squared. Okay, or x is equal to r cosine theta, and y equals r sine theta. Okay, well, again, that would be r and theta. We only have two. Okay, we only have two variables. Okay, we can't eliminate that third variable. In this case, it's y, by converting to polar coordinates. So we can either wait to convert to polar coordinates after we do the first integration, okay, you know, or we can just say, hey, once we convert to polar, we know that we're going to still have to integrate with respect to y first, okay, that's not going to have a polar substitute. So what I'm going to do is I'm going to I'm going to convert to polar right now, and we're going to see that yeah, we still have to integrate with respect to y. Y doesn't have a polar analogy. Okay, only x and z do. Okay, they have a polar, which is, but that's nice because, well, what is the square root of x squared plus z squared? Polar coordinates. Okay, or we could say y is equal to, okay, sorry. Okay, this function of x, y, z, okay, this function of x, y, z of the square root of, okay, x squared plus z squared, okay, that function, okay, we can replace with r and theta. Well, in this case, okay, so it would be f of y comma r comma theta, right? Again, the y doesn't go away. Okay, but the function that we're integrating over doesn't contain a y, so that's kind of nice. Okay, so what is this thing? Well, that thing is just r, right? So that's just r. Okay. Okay, so let's look at our converting this thing to polar coordinates. Okay. So the way I'm going to set this up is I'm going to go dy, dr, d theta. Now I did just change x and y to r d theta. So what do I need? What do I need to have an extra one of by going from rectangular to polar? Thank you, Giovanni. Yes, it's r. Okay, it's an extra r, right? RDR. Whenever we go from polar to, or sorry, from rectangular to polar, we must include that extra r. So I'm going to put an extra r there. Okay, that's an extra r. But what was my original function? Wasn't my original function an r as well? Right? So that's r times, I'm not going to multiply it just yet. Okay, that's r times dy, dr d theta. Okay, so again, you can easily see it, that's r squared dy, dr d theta. Okay, now what about the limits of integration? This is going to go from r squared up to 4. R squared to 4. Now, what's r going from? Well, r is just going from 0 to 2, right? 0 to 2. And what's theta going from? Well, isn't that just 0 to 2 pi? And so this became a much simpler problem, right? Okay, so let's integrate with respect to y in this case. Well, that's just going to be y r squared, right? So now we're going to plug in our limits of integration. So that's going to be 4r squared minus r to the 4th. Okay, and we're going to integrate this with respect to r theta, dr d theta. Okay, so that's 0 to 2 pi. Okay, so this becomes 4/3 r cubed minus 1/5 r to the 5th. Okay, from 0 to 2. Okay, so this becomes 4/3 times 8. Okay, minus 1/5 times 32. Okay, and so this is 32/3 minus 32/5. And when you get a common denominator and get that fraction, you get 64 over 15. Okay, and so that's just a number evaluated from 0 to 2 pi d theta. Now the number doesn't contain any thetas, so when I integrate that number, I just get theta. If I plug in the limit 0 to 2 pi, I can't draw. Okay, theta from 0 to 2 pi, it just becomes plugging in 2 pi, right? So this becomes 128 pi over 15, which is the correct answer. Okay. Okay, let's do one more of these since they are so much fun. Okay, it's nothing like doing triple integrals early in the morning. Okay, it is amazing. Okay, good times, good times. So let's do another one. Okay. Again, we're kind of stepping things up in difficulty as we go up here. Okay. I'm going to skip this page. Whatever, it's fine. Okay, so let's go. Let's find a volume. Okay. When I wanted to find an area before, okay, using a double integral, what did we do? Right? So the area over D of 1 dA is equal to the area, right? We just let the function be 1. Does that make sense? Because then we integrate with respect to 1, and then that just allows us to plug in our limits, okay, of integration. It means we're just integrating in 2 dimensions. Okay, we're integrating, okay, with respect to x, and then with respect to y, and then with respect to x, we're integrating, and so we get our total area that way. Okay, well, the same thing occurs when I integrate over E of 1 dV. That's going to get me my volume. Okay. So the first application of this is to find volumes of things that aren't too nice, right? So we can find the volume using a triple integral of solids that you know don't look too nice. Like in the previous example where we had that paraboloid, we could easily have let the function equal 1 and then just integrated, okay, that triple integral and found the volume, which is kind of cool. Okay, so you're like, well, what's the volume of a paraboloid? You're like, oh, well, now we have the tools to be able to find the volume of the paraboloid. Okay, okay, so let's use this idea of letting the function be 1 and getting the volume. Okay, using a triple integral. Okay, so let's go to number 4 here. Use a triple integral to find the volume okay, of the tetrahedron bounded by the planes x plus 2y plus z equals 2, comma, x equals 2y, okay, comma, x equals 0, comma, and z equals 0. Okay, so we're bounding this this plane here. Okay, so I'll just put up a rough sketch of this. What is this going to look like? Okay, a rough sketch. Okay, and so let's get our X, Y, and Z. Okay, and so yeah, so we have X equals 0, 0, Z equals 0. We're bounding that. Okay, so you know, and then you're like, well, which side of that is? It's going to be the positive side. Okay, so just go with the positive side for right now. We'll see that in a second once we get the plane. Maybe I don't want to do the plane first. I want to do this guy first. Okay, so maybe we'll just draw that line first. That is a line, right? That's just the line, you know, y equals 1/2 x, or x equals 2y. So what are some points on that line? That lies in the plane, right? This has no z component, so the z is essentially 0. And so this lies in this plane, this floor. Okay, the floor here, it lies in that floor, and it's the line y equals 1/2 x. Okay, or x is double y. Okay, so when y is 1, x is 2, right? So when y is 1, x is 2. And so we get this nice line. Okay, that's kind of not a nice one. I'll be a little OCD on this line here. Okay, let's see if I can manipulate this to do what I want it to do. Okay, so is that good? That's good. So that. Okay, so there's my line coming out. Okay, get rid of my ruler. Okay, and I could have extended that back if I want to, but I really just want to talk about the positive region for right now. Okay, and so this is the line x equals 2y. Okay, so what's happening with the tetrahedron? Okay, so the tetrahedron, okay, well, let's find the intercepts, right? What's the intercept for, you know, this tetrahedron when x is equal to, what is x when y and z are 0, right? So x plus 2y plus z equals 2. Well, x is equal to 2 when y and z are 0. So 2, right? So 2. Okay. What about y? Okay, what's y when x and z are 0? Well, y is equal to 2y equaling 2, so y is 1, right? So again, we're going to get 1, 0, 0. We get, or sorry, 2, 2, 0, 0. My bad. We get 0, 1, 0, and we're going to get 0, 0, 2. Okay, so one of these points is problematic, and I'll discuss that in a second. Okay, but z is up 2. Okay, and y is at 1. Okay, so if I were to, I'm just going to use dashed lines right now because we haven't included everything yet in this. Okay. The idea, though, is that this plane, x equals 2y, is a plane. It's not a line. It's a plane. It's a plane that's severing this tetrahedron. Again, so let me try to highlight this. Here's the tetrahedron that would exist without, okay, without the x equals 2y plane. But okay, with the x equals 2y plane, it gets severed. And so the point that I'm really interested in, okay, I don't want to do that. go back. Okay, the point that I'm really interested in is here. It's not the one on the x-axis because that doesn't exist, right? That point doesn't exist on my solid. This guy doesn't exist. He's problematic. We're gonna go right here, okay, right, where x is equal to 2y, okay. And so, you know, let z equals 0, right? So let z equal 0. So x plus 2y plus 0 is equal to 2. So x plus 2y equals 2, right? But what do we know? We know that this line, okay, is on x equals 2y. So let x equal 2y. So we get 4y equals 2, so y equals 1/2. And x would then have to be equal to 1. Okay, so this really is at the point 1, 1/2. So this is 1, 1/2, 0. Okay. Yeah, and not at 2, 0, 0. Okay, does that make sense? Okay, let me get rid of this guy here. Okay, and so that guy there, let's get rid of the highlighting. And so my real tetrahedron is just this piece. Okay. Is that piece there. Okay, pretty spicy stuff, huh? Spicing it up. Okay, so we know that we're going to plug this into a triple integral, right? Okay, to find the volume. So let's start setting up our triple integral. Okay, so first I want to figure out, well, what the heck does this thing look like? Where is this going from? You know, and so let's try to set up our triple integral. Okay, so I've got my triple integral, and then we're going to find 1, right, dv, because we're finding the volume. Okay, 1 dv. Okay, nice. Okay, so in this case, I'm going to go dz, right, dz first. dz first. I'm going to integrate with respect to my height first, because this is oriented the way that I want it to be oriented. It's cool, it's good. We're going to integrate with respect to z first. So I've got to figure out, well, where does this go? What surfaces is z bounded by? Right? Well, z is bounded by the plane z equals 0, okay, to, okay, this upper plane here. And so I can just solve this for z, okay, to z equals, okay, just toss everything to the other side that doesn't involve z, and we get 2 minus x minus 2y, right? Okay, and so z goes from 0 to 2 minus x minus 2y, okay, for that tetrahedron. Okay, now what about y? Let's look at y and x now, right? Y and x. So that's my dz. Okay, I actually probably should have created a new one below. So let's do that. Okay, so I'm just going to leave off the 1. The 1 is negligible. Okay, it's dz. Okay, and then 0 to 2 minus x minus 2y. Okay. Okay, so now I want to know, well, do I put x first? Do I put y first? It really doesn't matter, just whatever's easiest. okay, to set up. Okay, it does matter in this case because I don't want to have to do two integrals instead of one, and we'll get to that in a second. Let's look at our D now, our domain in the XY plane. Okay, let's look at D, which is our domain in the XY plane. It's the projection of the surface, okay, the top surface onto the XY plane. Okay, it's the base of my solid, basically. Okay, look at the D domain in XY plane. Okay, this is the base of my solid. It's not my solid. I don't own it. It's the base of the solid. Or we'll say it's the base of the tetrahedron. Okay, base of the tetrahedron. Okay, so we're going to look at this base now. Let's look at it in 2 dimensions. Okay, so we get X and Y. Okay, this 2-dimensional base. And what was it again? It was X equals 2Y, right? So every time I went out 1 in the Y direction, right, I went out 2 in the X direction, right? So X equals 2, that's wrong. I don't know what I'm doing here. Okay. I'm stuck on intercepts again. That is not intercepts. I don't think this is going to be nice to me. Nope. Okay. Let's just get rid of this. Okay. Oh. Start over. Okay. I need to draw a line. This is like algebra 1 skills. Come on. Let's draw our line. I'm talking to myself, by the way. It's like, get it together, Professor Holtman. Okay, so X is equal to 2Y. What is that line? That line is Y equals 1/2 X, right? So how do I draw a line equals 1/2 X? Okay, X goes out 2, Y goes up 1, and we get our line here. Okay. Okay, that's what's happening there. Now, let's go back to our tetrahedron. Okay, I want to look at this boundary line. Let's undo that. Okay. Okay, I want to look at, I'm going to use a different color. This boundary line, where is that boundary line occurring? Okay, well, I know that I have an intercept at y equals 1, right? We have an intercept at y equals 1. Okay. And we also know that there's a point at 1/1/2. Okay, 1/1/2. Well, where's 1/1/2? It's right here. And so we get this guy. Okay, and so I didn't draw this big enough. You'll forgive me for that. But the area that I'm looking at for D, my domain, is this. It's the green area here. It's D. Okay, that's what's being sliced off. That's what's being sliced off by my tetrahedron and my planes. This is the plane. Okay, that purple line is the plane X equals 2Y. And this purple line is the plane made by the tetrahedron, or made by the plane. I should probably just color code these. I don't know, I'm screwing up all over the place. Okay, so this is the plane. Remember, these are planes. They're not just lines. This is the plane X equals 2Y. This green line here okay, is the plane. It comes from the plane, okay. What was the original plane for the tetrahedron? It was x plus 2y plus z. X plus 2y plus z is equal to 2. Okay, that line there, okay, comes to us from that. Okay, so what is this line? Okay, in 2 dimensions. What is that line in 2 dimensions? Well, okay, wouldn't it just be this plane, but without the z coordinate? Right? Does that make sense? Okay, so this line here, let me enlarge the graph. Okay, since I didn't draw it well. Okay, so we have 1, 2, and then 1. Okay, and so this is 1/2 right here. 1/2. Okay, 1, 1/2, 1, 2, right? And so we're getting this point out here. Let me see if I can grab my ruler. Okay. Make my point a little bit bigger. Okay, and then we're going to be at 1/2. Let me grab my ruler again. Okay, and so we're going to want to integrate this. Okay, again, what is this guy here? And what is this guy here? Okay, this guy is x equals 2y. Okay, this guy here is going to be x plus 2y equals 2. Okay, that just equals x plus 2y equals 2. Okay, now I want to integrate, right? I want to integrate, find my limits. We're still just finding the limits. The limits of integration are tough. They're pretty tough on this one. Okay, I still want to integrate. Now, do I want to integrate with respect to x, or do I want to integrate with respect to y? Okay, do I want to solve these equations for x, which they're, you know, if I toss 2y to the other side, I can easily solve both of these equations for x, or do I want to solve them for y? Do I want to integrate with respect to x, or do I want to integrate with respect to y? Well, if I integrate with respect to y, I run into problems. Okay, if I integrate with respect to y, then I have to break it up into 2 integrals. I don't want to do that. That would suck. Okay, you know, if I integrate with respect to x first, then I have to break it up into 2 integrals. Okay, if I integrate with respect to y, then I only have to break it up into 1 integral. Okay. Okay, I don't have to add pieces. Okay. And so I really want to integrate with respect to y first. Okay, so this is going to be dz, dy, dx. dz, dy, dx. D's nerf. I don't even know what that is. It's some sort of French gun or something. I don't know. Whatever. Okay. If you speak French, there's a joke there somewhere. Okay. So dz, dy, dx. Okay. What do we say z was going from? Z was going from 0 to 2 minus x minus 2y. We got z done. Woohoo. Yay. What about y? Where's y going from? Well, we have to solve these equations in terms of y equals, in terms of a function of y. Okay, well, the bottom one is pretty easy. That's just y equals 1/2 x. So the bottom function is 1/2 x. Okay, what's the top function? Well, the top function, we have to solve for y. So this top function, y equals, toss x to the other side, divide by 2. That's negative 1/2 x plus 1. So that becomes negative 1/2 x plus 1. Okay, and there's a negative there that got lost. Okay, and then what does x go from? Okay, once I integrate with respect to y, okay, now what is the one-dimensional values for x going from? Well, it's going from 0 to 1, right? So 0 to 1. Okay, now we're ready to integrate. You're like, we just spent 20 minutes at trying to figure out how to integrate this thing, and we haven't even integrated yet. Yeah, exactly. But the integration is the easy part. Okay. So yeah. So the hard part of it is setting up the integral. Okay. The integration should not be too tough. Okay, especially since our function on z is just 1. Okay. So so again, this, I don't even want to tell you this. Okay. But what happens when we integrate this with respect to z? Okay, because you're gonna be mad. You're like, what? We didn't even need a triple integral? No, we really didn't need a triple integral here. We didn't. Why? Because let's just integrate on z. Okay, what happens when I integrate on with respect to z? Don't I just get z? Right? And what's that evaluated from? 0 to 2 minus x minus 2y. Oh, okay. Yeah, and what happens when I plug that in? Well, goes from 0 to 1 to 1/2 x to negative 1/2 x plus 1. And then plug this in. Well, that's 2 minus x minus 2y dy dx. Well, isn't this thing just a double integral over d? And yes, it is. That's just that's going to give me my volume, which we've done in previous sections. That's just going to give me my volume under the surface 2 minus x minus 2y, right? That's going to give me the volume under the surface. So it makes sense. Okay, so again, we could have done this problem with just a double integral, but we still would have had to go through finding out what the domain here for d is. Okay. But yeah, okay, it's kind of cool. Okay, so I mean, the math all works. It should all work together. One cohesive, world of mathiness. Okay, so now let's just do our double integral, right? So this is the volume of, or volume under f of xy equals 2 minus x minus 2y. That's the volume under this thing. Okay. Right? It's the volume under it, right? Where what? Where dy dx is dA, right? dA. This thing is dA. Ah, okay, cool. Yeah, nice. Okay, well, let's integrate with respect to y first here. So I'm going to get 2y minus xy minus y squared. Okay, everybody good with that? Evaluated from 1/2 x to, I'm just going to go 1 minus 1/2 x. That's okay. 1 minus 1/2. I just don't want to have to keep writing two symbols if I don't have to. Okay. Okay, so now what are we going to do? We're going to plug this in for y, right? Okay. I'll plug this in for y. Okay, so I get 2 times 1 minus x, or sorry, 1 minus 1/2 x. Okay, minus x times 1 minus 1/2 x minus 1 minus 1/2 x squared minus 2 times 1/2 x minus x times 1/2 x. Can I just simplify these? I'm just going to simplify these. This is x. Okay, you can do that in your head. And this is just minus 1/2 x squared. Just save some space. Okay, minus 1/2 x squared. The quantity 1/2 x squared. Okay. Good? So far, so good? Okay, so let's multiply all of this out, and some nice things are going to happen. Okay, distribute, I get 2 minus x. Distribute minus x. Okay, this is going to be plus 1/2 x squared. Okay, this is going to be minus 1 minus x plus 1/4 x squared. Minus, I'm going to distribute the negative sign, minus x plus 1/2 x squared plus 1/4 x squared. Okay, distribute the minus sign. 2 minus x plus 1/2 x squared minus 1 plus x minus 1/4 x squared minus x plus 1/2 x squared plus 1/4 x squared. Okay, so what's going on here? Okay, so let's combine all the like terms. We'll start with the x squareds. We have a 1/2 x squared plus a 1/2 x squared. Those two are going to combine into 1x squared. We have a minus 1/4 x squared and a plus 1/4 x squared. Those are going to cancel. So this just becomes x squared. Well, that's nice. Okay, let's continue. Okay, we have a negative x and a negative x, and then we have a positive x and a negative x. Those are going to cancel. So this is minus 2x. That's nice. And then we have 2 minus 1. Okay, that's going to become plus 1. That's nice as well. And that's all over 0 to 1. Oops. That's an easy integral. 0 to 1 dx. Easy peasy. Okay, so this becomes 1/3 x cubed minus x squared plus x from 0 to 1. Right, so just plug in 1. This becomes 1/3 minus 1 plus 1, which is 1/3. The whole thing is 1/3. The volume of that is 1/3. It's kind of cool. Which is kind of cool, actually. Because, you know, this is a pyramid, okay, and the volume of a pyramid is 1/3 base area times height. So that's kind of where you're getting that 1/3 from. If you're taking your base area times the height and you're slicing it into a third. So, so yeah, but I mean the base area is a triangle in this case, but you kind of get the idea, okay, that there's thirds involved because of the fact that this tetrahedron is a pyramid. Okay, so intuitively it makes sense that you would end up with a third of something. Okay. Okay, let's go back to center of mass. So let's finish up today talking about center of mass again. Okay, so we got center of mass, but we're going to do center of mass now, not of a lamina, but of a solid, the center of mass of a solid. Okay, so which is a little bit more useful than the center of mass of a lamina. Okay, lamina is just like a two-dimensional figure, and you're like, oh, well, where's the, you take a sheet of paper, and you're like, oh, where's the center of this sheet of paper? Okay, well, that's helpful. But then if you take a brick and you're like, oh, where's the center of mass of this brick? Well, that's a little bit more helpful in applications, right? So let's take the center of mass of a solid in this case. Okay, so X bar, Y bar, Z bar. Okay. Okay. Okay, X bar, Y bar, Z bar, which is where I'm going after this. I'm just kidding. Okay, that's a joke. Okay, X bar, Y bar, Z bar. Okay, equals, my humor is wasted on you people. Okay, M, Y, Z, so that's the moment, okay, the moment in the X direction, okay, the moment in the X direction over the mass, the moment in the Y direction over the mass, and the moment of the moment in the Z direction over the mass, okay, where the mass is equal to the triple integral of rho of x, y, z dv. The m of y, z is equal to x times rho of x, y, z dv. M of xz is equal to y rho xyz dv. Get rid of dv here. Okay, and then m of xy, moment in the z direction, is the triple integral of z rho of xyz dv. Okay, so there you go. So 4 triple integrals. Woohoo! Fun times, right? We're gonna do 4 triple integrals. Nice. Okay. Okay, so I don't think this is that difficult. It's just a lot of like grunt work, right? It's like it's a lot of grunt work. Okay, so I don't think this is rather that difficult, but it's a lot of grunt work. Just pushing through, right? I think Calc 2 is maybe a little harder than Calc 3, but Calc 3 is just like you're trying to push through, right? Just do all these calculations and not make any mistakes. You're not afforded any mistakes, especially on this next exam. Okay, you want to practice these triple integrals and double integrals a lot so that you get in the habit of being able to set them up and do the calculations, because again, you're not allowed mistakes on the next exam. Okay, you want to be able to say, hey, oh, I'm putting parentheses in the right place. I'm distributing in the right place. Don't make algebra mistakes. Okay, the days of making algebra mistakes for you guys are over. Okay, you're not afforded algebra mistakes at this point. Okay, so no, we're doing a lot of computation. Okay, okay. 5. They're the big leagues. Welcome to the big leagues. Okay. Okay, or in the words of Samuel L. Jackson from Jurassic Park, hold on to your butts. Okay, find the center of mass of the solid of constant density, oh, that's nice, of constant density rho bounded by the parabolic cylinder x equals y squared and the planes x equals z, z equals 0, and x equals 1. Okay, so we have a parabolic cylinder. Okay, so what does this thing look like? Well, it looks like this. Okay, we have our x, y, and z, right? So we have the plane. Is that x equals z or x equals 2? No, it's x equals z. Yeah, it's x equals z. Okay, so what does the plane x equals z look like? Let's deal with that first. Okay, that means that the plane x equals z is coming out like this. Okay. X equals z, right? So that's that plane there. It's just, we'll leave it like that. Okay, x equals z. Okay, it's a line in the xz plane, right? Does that make sense? It's a line in the xz plane and then it extends. Okay, so it's going to be hard with the y-axis here. Okay, but you get the idea. Okay, it's plane, extends. Okay, in the y direction. Okay. What about okay, it's a bounded by the parabolic cylinder of this x equals y. What does x equals y squared look like? Well, that's if we were to get rid of, if we were just looking the xy plane, not let z be anything. Okay, it's just a parabola. It's this parabola here. Okay, does that make sense? It's that parabola there. I don't know, making a mess. Messing it all up. There we go. Okay, that's that parabola I ate. Okay, and maybe I'll make another one up here. Okay. Okay, and then the plane x equals 1. Well, where's the plane x equals 1? Right, z equals 0 is going to be above then the positive z region. Okay, the positive z region, right? This is going to go above instead of below. Okay, so we've knocked this one off. We've knocked off what's x equals z. We've knocked this one off. Let's do x equals 1 now. Okay, how's that gonna? Well, that's just a plane. Okay, that's just gonna, right? So that's gonna kind of slice down here. Okay, x equals 1. Okay, and so I'm going to do it this way. Do this. Nope, I'm not going to do that. I'm going to do this. There we go. And I'm going to do this. This thing should be more like this. Okay, and then like that. And now I'm going to go up. Okay, with the little slice there. And so what I'm really getting, okay, is I'm going to get rid of everything that really, truly doesn't exist here. That doesn't exist. That doesn't exist. That doesn't exist. And so we kind of get something that looks like that. Okay, it's a little wedge. That's a slice with a parabolic ceiling here. Okay. And so we get that. Okay, but again, I want the projection of this. I want the projection of this in the XY plane. Okay, because that's what we're going to use to get our domain here. Okay, D. Okay, so find the center of mass, okay, of this thing. Well, what is the mass first? The mass is rho, okay, times dv, right? So dz, we're going to do dx, dy. Okay, so what does z go from? Z goes from, okay, 0, or sorry, not 0. It goes from, yeah, it goes from 0 to x, right? Oh, z goes from 0 to x. Oh, it's not that wedge. It's the bottom wedge. My bad. It is this. It is this here. The top one doesn't exist. I'm sorry. There we go. I don't know. It's kind of hard to see. But, okay, the top one. So that's my domain. Okay, but the volume is this wedge. So it does go from 0. It goes from 0 to x, z equals x. So maybe a side view would be better of what the hell I'm trying to draw. Okay, so here's this thing, here's the base, okay, and then up, right, and then it gets cut off, and so then we have this z equals x plane. Okay, I don't know, I'm still screwing it all up. Okay, but you get the idea. How could I draw that better? Let me try one more time. Okay, so let's go like this. up like so. Okay. Let's go down like so and go over and go up. Okay, but the traces are parabolas. That's better. Is that better? I think that's better. Okay. Let me put in my axes. This is X. This is Y. Go away. Go away. Go away. Go away. Go away. There we go. Okay. Z. Okay. Is that good? Does that help? This is crap. Okay. So forget it. I gotta watch my language because everything's being recorded. Okay. So does that help? Does that make more sense? That should make more sense. Okay. This is actually a plane. Okay. That's slicing this thing, but you get it. Okay. It goes, okay, Z goes from Z equals 0, okay, to Z equals X. Okay, that's a boundary here, Z equals X. Okay, what about X? What's X going from? Well, the reason I let it be X and not Y is because of our function, X equals Y squared, right? This is a sideways parabola, if you were to look at it in the XY plane, right? This is a sideways parabola. And so it's just easier to say, well, you know, let's integrate with respect to X first, right? But where's the cutoff here? Where's the cutoff? The cutoff is 1, right? So X is going to go from Y squared to 1, right? So X goes from Y squared to 1. And then what does Y go from? Well, this is the point 1, 1. This is the point 1, negative 1. And so where does that? Well, the Y is going to go from negative 1 to 1. Okay, does that make sense? Sounds good. Okay, so again, the hardest thing of these is setting up the secant integrals. Okay. Okay, so let's integrate with respect to Z first. So that's going to be rho Z, 0 to X, plug in my X, that becomes rho X. Okay, where rho is just a constant. I could actually just pull this rho all the way out in front if I really wanted to. I don't want to though, because sometimes I forget that the rho is there and I forget to carry it down. So I'll just keep it with me, keep it close so I don't forget it. Okay, so now we're going to go from Y squared to 1, and this is negative 1 to 1. Okay, and then we're going to do dx dy. We're going to start chopping this thing down. Now let's integrate this with respect to X. That's 1/2 rho X squared, Y to 1. Plug in, this is 1/2 rho minus 1/2 rho Y squared. Sorry, this was Y squared, not Y. So this is Y to the 4th. Okay. Yeah. Okay, I can factor out my 1/2, and this is now negative 1 to 1 dy. I'm going to factor out my constants here, which are 1/2 rho. Okay, negative 1 to 1. This is 1 minus Y to the 4th. dy. Integrate with respect to y, we get y minus 1/5 y to the 5th. Nice, nice, nice. Okay, and that's from -1 to 1. So this becomes 1 minus 1/5 minus -1 plus 1/5. This becomes 2 minus 2/5, which becomes, and again, I don't want to forget this. There's a 1/2 row on the outside. Okay, 2 minus 2/5. Okay, that's 1 3/5, which is 8/5. So this is 8/5. Okay, and then this is 1/2 row. So cancel, and we get 4 row over 5, and that's the mass. That's the mass. Okay. Okay, so you're like, well, yay, we found the mass. Nice. Okay, well, let's do the first one of these real quick. Let's find the moment. Okay, the moment in the x direction, moment of yz. That's the triple integral of x rho dv, right? Well, we did a lot of the heavy lifting already in just finding what the limits of integration are here, right? So we found those. That was the hard part. This is 0 to x. Okay, actually, I'm going to write it on the next line. Excuse me. Okay, x rho. This was dz, dx, dy. Okay, 0 to x. This was y squared to 1, and this was 0. It was, sorry, -1 to 1. -1 to 1. Okay. So with respect to z, this is going to be xz, 0x. That's going to give me an x squared. Okay. Integrate with respect to, x squared rho. Integrate with respect to y. Okay, dy. This is going to become x squared rho y from y squared to 1. So this becomes, no, that's wrong. It's with respect to x and what I'm doing. Okay, with respect to x. And so this becomes 1/3 x cubed rho evaluated from y squared to 1. Okay. So this becomes 1/3 times rho minus 1/3 rho times y squared to the 3rd is y to the 6th. Okay, now integrate that from -1 to 1, dy. This becomes, again, I could factor out the 1/3 row if I want to. 1/3 row times the integral of 1 minus y to the 6th from -1 to 1. This becomes y minus 1/7 y to the 7th from -1 to 1 of 1/3 row. Again, my rows look like e's. Okay. Rho again is my density. It's a homogeneous density in this case. Okay, and so plug in 1 here. We get 1 minus 1/7. Okay, plug in -1, we get -1 plus 1/7. So this becomes, again, 2 minus 2/7, which is going to be 1 5/7, which is 12/7, I believe. Maybe? I don't know. Let me think about that for a second. 1 5/7. Yeah, which is 12/7. Okay, times 1/3 rho. Okay, and then cancel, and I get 4 rho over 7, which is correct. Okay, so that's m of x, of course, m of y, z. Okay, so we found that, but then in order to get x bar, okay, what is x bar? Well, x bar is going to be 4 rho over 7, it's m of xy over m, right? All over m. Well, what was m again? From the last one, that was 4 rho over 5. 5. The 4 rows cancel, and I'm just left with 5/7 as the center of the x values. Whew, that was fun. That was spicy. Okay, now what do we have to do? We have to do this 2 more times. You're like, joy, yay. Well, guess what? You're not in this class to make your life easier. Okay, you're in this class to make your brain smarter. And so what are we going to do? We're going to exercise those integration muscles. Ooh, yeah, we're going to do some reps, right? We're gonna do 4 reps here. Okay, so yeah. So actually, we're not. I'm going to do 1 more, and then I'll let you guys do the last one. Okay. So let's figure out what y bar is. Okay, y bar is equal to m, okay, of xz all over m. Nice. Okay. So let's find m of xz. This one's kind of a nice one. Okay. Maybe we'll do all 3. Maybe we have time. We have time. That's fine. Again, the more integration you do, the better. Okay? It's like eating your vegetables. Do your integration. Do those push-ups. I want to see 40 integrations done. Drop and give me 40 integrations. Okay? That's what I'm saying. Okay. This ain't your grandma's math. Okay? This is some serious stuff. This is a serious, this is marine math. This is oorah. Okay, say your oorahs. Oorah. Okay, this is the good stuff. Okay. Anyway, I'm losing it. Okay, it's the cabin fever. mxz over m. Okay, so let's find m of xz. Okay, real quick. M of xz, okay, is what? Well, it's -1 to 1. Okay, y squared to 1 of y rho of, oops, I forgot my last one. It's 0 to x. Okay, of y rho dz dx dy. dz dx dy. Okay. So with respect to z here, that's just going to be y rho z, right? Okay, y rho z. Okay. Yeah. Okay, I don't know. Okay, so this is from 0 to x. Okay, plug in for x. So we get xy rho, not e, rho. Okay, and we want to integrate that y squared to 1 with respect to x. Because it comes 1/2 x squared y rho from y squared to 1. Okay, so this becomes 1/2. Okay, plug in here. This is y to the 4th y rho. No, what am I doing? Plug in the 1 first. 1 squared y rho minus 1/2 y to the 5th, but we'll do y squared y rho. Okay, so this is 1/2 y rho minus 1/2 y to the 5th rho. Okay, and now I want to integrate this from, knock it off. Okay, -1 to 1, okay, dy. Okay, 1/2 y, okay, rho, I'm going to integrate that with respect to y. This becomes 1/4 y squared rho, okay, minus 1/12 y to the 6th rho from -1 to 1. Okay, plug in 1 for y. I get 1/4 rho minus 1/12 rho minus, and plug in -1, it's the same thing. So we're actually getting something minus itself. That becomes 1/4 rho minus 1/12 rho. That becomes 0. That's kind of nice. Okay, so on with respect to y, okay, the thing is 0. Okay, or the the center of mass, okay, the center of mass in the y direction, okay, is equal to 0. Now, that shouldn't come as too much of a shock if you look at the diagram before, and we'll go back to that in a second. Okay, so y prime is 0 over m, right, which is 0. So that y value, okay, again, let's go back to the diagram that I drew. Okay, this one here. And why does it make sense that the center of mass would be 0 for the y's? Well, it's because of the symmetry of the paraboloid, right? Does that make sense? So the symmetry of this paraboloid means that it's symmetric, it's balanced. It's got this, it's the parabola has symmetry. Okay, it has symmetry. And so with respect to y, yeah, the center of mass should be 0, right? Because it's balanced, right? You got the same amount on one side of y as you have on the other side of y, and so it is balanced. And so where is your center going to be? Your center is going to be at y equals 0, or the x axis, or in this case, the x plane. Okay. Yeah. Okay, or the y equals 0 plane is what I should say. Okay, it's balanced with respect to that. Okay. Okay, let's do the last one. Okay, let's find z prime or z bar. Okay, and then again, I guess it's fitting that we're ending on z bar, because then again you can't go to by the way, you can't go to z bar, okay, because of social distancing. I'm just letting you know that. Okay, so don't even try to go to z bar. Okay, they're closed. They're all closed for good reason. Stay inside. Stay away from each other. Okay? Okay? Stay away. Okay, anyway. M of xy over m, right? So we need to find out what's m of xy. Well, m of xy is my triple integral with respect to z. Okay, with respect to the z z coordinates of dv here. dv, oh, sorry, there's rho as well. Rho dv. Okay, and so again, let's do our final triple integral here. So this is 0 to x, I believe. Yep, and this is y squared to 1, and this is -1 to 1. And then this is z, and then this is dz, dx, dy. Okay, so this is going to be 1/2 z squared rho. Okay, value weighted from 0 to x. So this is going to be 1/2 x squared rho. Okay, integrate y squared to 1. Okay, dx. This is going to be 1/6 x cubed rho, y squared to 1. This becomes 1/6 rho minus 1/6. Okay, 1/6 rho minus 1/6 y to the 6th, right? 1/6 y to the 6th. I believe that's correct. Rho, sorry, rho. Don't forget the rho. Okay, and we want to integrate that from -1 to 1 on dy. This is going to be 1/6 y rho minus 1 over, what is this, 42? Okay, y 7th rho from -1 to 1. Okay, cool. Okay, and then 1/6 rho minus 1/42 rho, right? 1/6 minus 1/42. Okay, plug in -1 this time. We get a -1/6 rho and then a positive 1/42 rho. Okay, cool. Okay, so this is going to be 1/6. There's a minus sign here, sorry. This is going to be 1/6 plus 1/6, which is 1/3 rho. This is going to be -1 over 42 rho minus 1 over 42 rho, so that's 1 over 21 rho. Minus 1 over 21 rho. Okay, multiply both top and bottom here by 7. And we get 6 over 21 rho, reduce, and we get 2 rho over 7, and that's z bar. Or sorry, that's not z bar. That's m of xy, right? That's m of xy. Okay, z bar is when we put 4/5 rho, nope, again, that's wrong. Let's put this up here. Mxy over m. So this is 2 rho over 7 all over 4 rho over 5, right? Okay. So the rows are going to cancel. The 4 and the 2 are going to cancel. Okay, and so this becomes 5 over 14. That's z bar. So what's my center of mass? My center of mass is 5/7, 0, and 5/14. That's my center of mass. Nice. Okay, and that's it for today. We did some good integration. Okay, practice this on your homework, and I will see you on Tuesday. I think, yes, Tuesday. Okay, If you have any questions, let me know.
There's a quick question about the test.
Yeah.
Um, is it going to be based on like how? Because you said it's going to be on WebAssign. Is it going to
Yeah.
be like how the WebAssign assignments are, where it's like you need to fill in blanks during the steps, or is it just like
No, there's no steps.
you just show the answer?
It's just fill in the answer.
Oh, okay. And we get 3 shots at that, right?
And you get three, well, yeah, you get 3 shots at the total test, not 3 shots at each individual answer.
Oh, okay. All right. Thank you.
Okay, yeah.